Good day, my angels. Here is the solutions to Lesson 3 multi-step momentum questions. Again, I miss teaching all of you very much right now. I hope you're all doing well. So let's get to the physics at hand. Key ideas. We're realizing that we can use the idea that impulse or change in momentum can be calculated by going final minus initial if I use mv for momentum. Impulse can be calculated by just going the final momentum minus the initial momentum if I happen to know them. And change in momentum or impulse can be calculated by going force times time. And again, I'm being careful with my vector notation. I'm putting the arrows in because you'll notice in the homework there was some changes in direction. Let's look at number 1 from lesson 3. Let's see if we can do 1, 2, and 3 in one step. Car with a mass of 1,000 kilograms is at rest. That's important. It gives me a VI at a stoplight. When the light turns green, it's pushed forward by a net force of 2,000 newtons for 10 seconds. Forwards is positive, backwards is negative. Okay, first thing it wants is the acceleration. I think here I would just go A equals F over M. It's a net force, so I don't need to do a free body diagram. And they did tell me the force, it's 2,000. And they did tell me the mass, it's 10. And I can even do that in my head. The acceleration is 2.0 meters per second squared if you want me to add a direction forward, although it just said the value. I'm not sure it wanted the direction. What's the value of the change in velocity? Well, change in anything is final minus initial. So the final velocity is, I don't know. I'm going to have to figure it out. Okay. So V final equals V initial plus AT. It does say at rest. I just figured out A in part A, and T is 10 seconds. Hey, V final is 20, so it's going to be 20 minus 0. The change in velocity is, not meters per second squared, just 20 meters per second. What's the value of the impulse? I think to do that, to calculate that, I'm going to use this definition of impulse, except I'm going to be a bit lazy. I'm going to recognize that impulse, which is another word for change in momentum, is mass times the change in velocity, which I just figured out in number 2. The mass is 1,000. The change in velocity is 20, so the impulse is 20,000 kilogram meters per second. This car had a change in momentum, a gain in this case, of 20,000 kilogram meters per second. Number 4, what's the value of the change in momentum? This is a trick question because I already answered it. Number 3, I found the impulse. Impulse is another word for change in momentum, so the change in momentum is going to be the same as answer number 3, 20,000 kilogram meters per second. And now that I know that, I can start to combine some of these and probably save myself some time. What's the final velocity of the car at the end of the 20 seconds? Well, I calculated that, didn't I? It was V final was equal to V initial plus AT. It was at rest plus 2 times 20, no, times 10, Mr. Dueck. It was 20 meters per second. The car continues at this same speed for a while, so I guess we've eased up on the accelerator and now we're going at a constant velocity. Oh yeah, it does say constant velocity. So what's the value of the change in momentum? Well, if it's not speeding up or slowing down, there is no change in momentum because the momentum is constant. The value of the change in momentum is 0. And what's the value of the impulse? Same question, same answer. It's 0. You could put kilogram meters per second if you wanted to. Because impulse is a changing momentum. If your velocity and your mass aren't changing, then you don't have a changing momentum. You've got momentum, it's just not changing. The brakes are applied to the car, causing it to come to rest in 4 seconds. What's the change in momentum? I think here, to find the impulse, I'm actually going to use final minus initial, because my final momentum, if I come to rest, is 0. And my initial momentum was mv final. Sorry, it's going to be mv initial when I start hitting the brakes. It's going to be mass, which was what was it? I got to go look up the numbers. 1,000? Times the velocity when I started hitting the brakes, which was 20. So I get an impulse of negative 20,000 kilogram meters per second, which makes sense. The car has 20,000 kilogram meters per second of momentum. To come to a stop, it has to lose all of that. It has to undergo a change in momentum of negative 20,000 kilogram meters per second to go to the stop, to come to a stop. So what's the value of the impulse? Same answer. What's the value of the average force? The reason it's at average force is when you hit the brakes, probably the force actually isn't constant, but we can't handle a changing force. So average force. Since I know the impulse, I can go impulse equals force times change in time. I can say the force equals the impulse over the time. So it's going to be negative 20,000 over 4, and I get negative 5,000 newtons. 5,000 newtons backwards. You could also have gone F equals ma, and you could have found A, because you know T, you could have gone A equals VF minus VI over T. VF is 0, VI is 20, T is 4, and you'll get the same, and then multiply that by the mass, and you'll get the same answer. Oh, well, you know what? Number 11 asked me to find the acceleration. I'm going to go A equals F over M. It's 5,000, negative meaning backwards, divided by 1,000, negative 5 meters per second squared, or 5 meters per second squared. Backwards. Pardon me for the cough. This car slowed down at a much greater rate than it sped up. Number 12. Oh, wrong button. Determine the momentum change of the soccer ball. This is a trick question because impulse is the same as momentum change. So the fact that they gave me the impulse of 25 Newton seconds, that means the change in momentum is 25 Newton seconds. Or you could say 25 kilogram meters per second because those units are interchangeable. Trick question. Number 13, they want me to find the force. Okay. So I could absolutely find the force by going F equals ma, and then by finding A, and then using A equals VF minus VI over T. All doable, and I will give you full credit if you do that. But the impulse equation lets me do this in one line by letting impulse equal impulse. And what I really mean by that is force times the change in time equals mv final minus mv initial. Because then to get the t by itself, I do that, and I can get there in one line. It's going to be mass 1200, velocity final 10 minus mass 1200, velocity initial 25, all over 5 seconds. I get 1200 times 10 minus 1200 times 25 divided by 5, and I get negative 3,600 newtons, or 3,600 newtons backwards. We're slowing down. Number 14. Football question, because there's collisions in football. A 90-kilogram tight end moving at 9 meters per second encounters a 400 Newton second impulse. Determine the velocity change. Okay, well, another way to calculate impulse is mass times change in velocity. In fact, that's one of the equations that I gave you on your formula sheet. So if I want to find the velocity change, it's just going to be divided by the mass. The change in velocity is going to be 400 divided by 90. Mr. Dueck, what about that 9.0 meters per second? Turns out I didn't need it. And I get 4.44 meters per second. That's the change in velocity. Number 15. I said you could skip it. I'll do it anyways, just in case some of you tried it because you wanted extra practice. Again, it wants me to find the force. I could totally do this by going F equals ma, A equals VF minus VI, but I can do this in one line by saying impulse equals impulse. Change in momentum equals change in momentum. And then to get the F by itself, just divide by the change in time. I get 0.1 times 0 minus 0.1 times 40 divided by 0.025. I probably didn't need to type the 0.1 times 0, minus 0.1 times 40 divided by 0.025, and I get negative 160 newtons, or 160 newtons backwards. This might be when the puck is hitting the goalie, for example, and so it's coming to a stop. The force on it would definitely be backwards. 16, I also said to skip. I said it was nasty, but we can handle it. This is going to be several steps. So I'll do it in case you tried it. A hockey puck is at rest. It encounters a force of 20 newtons east, So since I see the word east, I'm going to call that positive. East is positive. Resistance force, so this is going to be negative. Finally, it encounters a final force in the direction of motion, so that's going to be positive. What's the final velocity of the puck? So it looks like we have three sections. Initially at rest, I want to find V final. I think I can go like this. Force times time equals mv final minus mv initial. In this case, since v initial is 0, it's just going to cancel out. V final is going to be force times time over m. It's going to be 20 times 0.2 divided by 0.1. The final velocity for the first bit of motion is going to end up being 20 times 0.2 divided by 0.1, 40 meters per second. Now let's walk here, and now V initial is 40 meters per second. Time is 2 seconds. F is negative 0.4 newtons. Okay, I can find V final again. Again, it's going to be force times time equals mv final minus mv initial. This time, unfortunately, one of the v's doesn't cancel, so I'm going to have to rewrite this equation to get the v final by itself. That's what I want to get by itself. Well, the force times time will drop down like a domino, and I think I would plus the mvi over. That would give me mv final by itself, divide by m. V final is going to be negative 0.4 times 2 plus 0.1 times 40, all divided by 0.1. And so in that middle section, negative 0.4 times 2 plus 0.1 times 40 divided by 0.1. We're going to slow down, so I should get an answer less than 40. Hey, 32 meters per second. And that's going to go scooching over here, because now VI is 32. We're going to get the same equation as before. We're going to get VF equals force times time plus m V initial all over m. This time the force is 24, and it's positive because it's in the same direction that we're moving. 0.05 plus 0.1 times 32 divided by 0.1. V final equals bracket 24 times 0.05 plus 0.1 times 32, close off the top, divided by 0.1. I know we sped up, so it should be bigger than 32. Hey, it is! 44 meters per second, and I got a positive answer, and I let east be positive, so there you go. I would not give you one this long on a test. Probably not even on a quiz. But it's doable. Back to the actual homework that I assigned. 17. Looks like number 17 is asking me time. Okay. Oh no, A, it's got an A and a B. First A, I forgot to put the letter A in the question, but clearly that's part A. It wants the impulse. Alrighty, so A, Another word for impulse is the change in momentum. Let's see, they gave me a mass. You know what? Here's a V initial. Here's a V final. I'm going to use mv final minus mv initial. So it's good. Oh, and V final is 0. Yay! So it's going to be negative 70 times 20. It's going to be negative 1400 kilogram meters per second. Or you could use Newton seconds. They're interchangeable. Or you could say backwards. Instead of negative. B. If this impulse is provided by the water exerting an average force of 280 newtons on the skier, how long should this force act? By the way, I guess if this force is slowing the skier down, it's going to be a negative because it's in the opposite direction of motion. I just found the impulse. I think I can go impulse. Let's go black. Impulse equals force times the change in time. So I think time is going to be the impulse divided by the force. It's going to be negative 1400 divided by negative 280. It's nice that the negatives cancel because time is a scalar. I should get a positive answer. And I think it's going to be 5. Oh, I got the answer right there, but let's double check to make sure the answer key is correct. Yep, 5.0 seconds. Number 18. How do seatbelts and airbags protect car drivers in a collision? Okay. Well, in any car accident, typically the final momentum is 0 because you come to a stop. So typically in any car accident, you have to absorb all of the impulse. But since impulse is force times time, as the time of collision increases, the force decreases. So seatbelts lengthen the time of collision. So do airbags. Crumple zones on cars lengthen the time of collision. Those big water barrels that you see in front of a cement barrier along the freeway, those are designed to absorb some of the momentum and lengthen the time of collision like a crumple zone does. Number 19. Wants me to find the impulse acting on the bullet. Oh, that's not too bad. Impulse, another word for which is change in momentum. It's going to be delta P, and it looks like I'm going to go mv final minus mv initial because I see a final and an initial velocity. It's going to be 0.015 times 200. You know what? From rest, so initial is going to be 0. 0.015 times 200, probably 30, isn't it? 3, sorry, I was off by a decimal. 3.0 kilogram meters per second. B says find the force on the bullet. So I would like to go force times time because I know the impulse, but I don't know the time. So I'm going to wimp out. Rather than doing it this way, I'm going to go F equals ma because I've got to calculate something, either time or acceleration. I may as well get there in one step and just calculate the acceleration. So the acceleration is going to be vf squared minus vi squared all over 2d, from good old vf squared equals vi squared plus 2ad. So it's going to be 200 squared minus 0 squared all over 2 times 1.2. I'm expecting a pretty big acceleration because it's a bullet. 200 squared minus 0 squared won't make a difference at all. 2 times 0.12. I get an acceleration of 1.67 times 10 to the 1, 2, 3, 4, 5 meters per second squared. And now I'm going to walk over here. F equals 0.015 times 1.67 times 10 to the 5th, although you know I'm going to use my answer button. And I get 2,500. Oh, did I miss a decimal? Oh, I missed a decimal here. This is wrong. Arg. Okay, let's go back. I got the decimal in the wrong place here. It's not 0.12, it's 1.2. You were screaming at YouTube, weren't you? It's 1.67 times 10 to the 4th. To the 4th. And if I go that times 0.015, I get 250 newtons. I never make mistakes. Number 20. Ooh, challenging question, but a cool question. This is the same physics as bouncing a basketball, bouncing anything on the floor, bouncing on a trampoline, where you rebound off of the ground and change direction. And what I said to you for this one is you want to let one way be positive and one way be negative. So I'm going to let up be positive. I'm going to let down be negative. And they want me to find the force. I'm going to use the idea that impulse equals impulse. That force times time equals mv final minus mv initial. And then to get the F by itself, I just divide by time. Again, you could totally find the acceleration and go F equals ma. What's the mass? Well, it's 75 marbles, 35 grams each. So the total mass is going to be 75 times 0.035. V final is 4 minus 75 times 0.035. V initial is negative 8. And then the time, I was a bit sneaky. It says per minute. Hey, that's 60 seconds. You can see why I kind of like the impulse equation. It's a lovely shortcut. One line and I'm done. Didn't need to bother finding the acceleration. I didn't need to bother going F equals what, ma. I got there in one fell swoop. Let's type this one very carefully, Mr. Dueck. 75 times 0.035 times 4 minus 75 times 0.035 times negative 8 divided by 60. Mr. Dueck, why was the mass 75 times 0.035? Because the total time involved was 60 seconds, and in that 60 seconds, it was 75 marbles that hit the floor, and so the total mass is 75 marbles. And since each one weighs 35 grams times 0.035. And I get, woohoo, F equals positive 0.525 newtons. So if you want me to give a direction, up. If I got a negative answer, this would have been down. I said you could skip the Calvin and Hobbes questions. 22. Okay. A tennis ball is traveling 40 meters per second when it bounces off of a wall, like some of you in my classroom. Bouncing off the... Well, no, nothing. when it bounces off a wall and travels in the, okay, this is a good trigger word, in the opposite direction that it came from, that means I need to let one way be positive and one way be negative. I'll let final be positive and I'll let initial be negative because I don't know whether this ball was moving to the left, to the right, north, south. And I know that if I let final be positive, the math usually is a bit easier, and you'll see why in a second. A, what's the change in momentum or the impulse? Well, that's going to be mv final minus mv initial. It's going to be m 0.095 v final 30 minus m 0.095 v initial negative 40. Can you see why I let initial be negative? Because that gives me a minus minus, which is a plus. 0.095 times 30 minus 0.095 times negative 40. Doesn't matter which way you let be negative and which way you let be positive, but you have to let one of those be negative and one of those be positive. I get positive 6.65. That's in the direction of the final bounce backwards. Kilogram meters per second. B, what's the average force? Well, they gave me a time, so I'm going to go force times time equals impulse. I'm going to go force equals impulse divided by time. So it's going to be 6.65 divided by 0.05. And I get 133 newtons. I got a positive answer. That's in the same direction as that final rebound. Kilograms, what you do? Newtons. And again, a nice shortcut. I absolutely could have gone F equals ma, and I could have solved for A, but I was able to do this really in one line plug and chug because I used the impulse equation. I didn't assign the hockey question. It's really, really similar to question number 22, only here I would find the impulse by using force times time for part A. And then I could find the force in part B. What force did the goalie apply? So the part A is the force that the hockey puck felt when it was hit by the slap shot. Part B is the force that the hockey puck felt when it came to a stop. Alrighty. And I'll email out the solutions sometime today, and you're getting also another Whoa Wednesday. Miss you all very much.